Yes, Srinivasan.
Yes, sir. Good evening.
Good evening. You're able to hear?
Yes, sir. We are able to hear you.
Okay. Uh, Fine. So I have my computer also. If I have to show a MATLAB program, that also I'm having it. Hey, Joseph, only only one person has joined. What happened to others?
I think they are. I guess they. I guess they would join because.
Yeah, Dr. Sundar said he would join, and he has gone through it. And
Okay.
he was telling that he had some doubts, so I would wait to listen to him.
Yes, sir. Yeah.
Joseph?
Yes, sir. Yes.
Video. Hello, Karthik.
Good evening, sir.
Good evening.
Yes, sir.
Have you seen at least for 2 classes? Hello.
Yes, sir.
Sir, there is echo.
I mean, when I talk, there's an echo.
A little bit, sir.
Now it's fine. Like, earlier there was there.
Yeah. Now,
Yeah.
now it's a little
Karthik,
bit.
have you seen?
I've
Have
I
you
saw
seen the
part of
previous
it.
videos?
I saw the video,
Part of
but
them.
I've seen the video, but I have to go through it in detail again, sir, which I will do today and tomorrow. I went through it yesterday and today,
You're
but
going to find
I
it
have to spend.
difficult.
Sure, sure. Sir.
We're going to follow what we are going to say. So that is a. Okay, we'll run through a bit. I'm just waiting for uh, Sundar. Once he has joined, we will start, right? Because he told me he
Joined,
wants
sir.
to
I have
raise some
joined, sir.
questions and so on.
I have joined, sir.
Oh, you have joined. Fantastic.
Yes.
So, Arjun has joined. Joseph?
No, sir. I can't see him.
Yeah, just send a message to him. We'll
Yes,
start
sir. Yes,
and
sir.
just put it in the group because Dr. Shanti has joined.
No, sir.
Yeah. Okay. Dr. Sundar, what we'll do is we will just quickly 10 minutes. We'll run through the whole thing. What we are trying to do.
Yes, sir.
Okay. And then you stop me whenever you need.
Yeah. Yes.
And
Yes.
Karthik, if you have gone through it, if you just stop me whenever you want a clarification.
Yes, sir.
Okay. So, so what is that we were doing? Actually, I was taking an example uh, in pharmacokinetics and pharmacodynamics just to illustrate how mathematics is used. Okay, and these examples are simple examples. The reason why I've not taken physiological examples is that it is slightly more involved and difficult. So that's the reason why I have not taken them right now. So, uh, so what is our major aim? The major aim is, if you remember, is to write a differential equation and then solve the differential equation for concentration. So I'm just going back to my one of the earlier classes where uh, we said that if there is a curve or a function which is as a curve, we can find out the slope at various points. On the other hand, that is function, given function, say for example C versus time, concentration versus time. So in plasma, then dC by dt is what we were looking at. Now you can go the other way and find out if there is a differential equation for dC by dt. If there's an equation for dC by dt, then can I find out C? Most of the times, that is how we proceed. And this is called as differential equation. And if the most of the equations are also what is called as ordinary differential equations, because we will see partial differential equations. So ordinary differential equations means that is abbreviated as ODE, ordinary differential equation. There are applications of another set of equations called partial differential equations that is very complex. We will not introduce all those things right now. So our job is to understand calculus, and with this we will close calculus and move to what is called as linear algebra and other things. So our job is to understand what these equations are. How do I put down the equation? So more important for you is putting down the equation. So in fact, last time Joseph had a question, so I had solved one of the differential equation in a classical way, but I'm not going to repeat it. But the more important thing is how we are going to uh, process this thing, or sorry, not process. How do you write these equations? So let us say, so the pharmacokinetic models, PK models, are all compartment models. The compartments are one where it need not be a physical compartment where the drug, for example, drug concentration is uniform. So this is what uh, we call as a compartment. Now, the example which we had taken is that um, suppose there is a. Well, Bhagyam has also joined. Is she there? I'm not able to
I've
see.
joined. I've joined. I've
Yeah, she has
joined.
joined. Okay. Yeah. Very good. So we have to write the differential equation. So, for example, let us say how uh, we are going to write down an equation for a drug to act on a tumor. Okay. So pharmacokinetics deals with how the drug is actually carried forward, and the role of the body on the drug. And then pharmacodynamics is how the drug is going to act on the body. So let us say that we give a dose of DA, okay, sorry, A, that is the dose that is given, okay. Of that dose that is given, a part of the dose is absorbed, okay. So that is called as absorption rate, K01, as you can see it. So that is the absorption rate, okay. So the absorption, after the absorption, it goes into we are talking about the, it goes to the next compartment, okay, which is goes into the plasma, and then it metabolizes. That is the third compartment, which is called, so you can see metabolite concentration, and the drug metabolite uh, at some rate and so on. So then there's a concentration of the metabolite, which is called as C2. So the next step is that this this drug, after this step, metabolite metabolizes, it acts on two things. One is on the tumor, and the other is the tissue. So you can say that the tumor, when it acts on the tumor, it is say the efficacy of the drug, and when it acts on the skin, tissue or so on, we can call that as the safety of the drug. So when it acts on tumor, we'll call that as efficiency. And drug and tissue, this is safe. Now there are various terms. One is what is called as the absorption rate. Okay, so look at how we are writing down the equation. So I give a dose A, and then once I give this dose A, a part of the dose is absorbed. So when the doses are absorbed with time, then there is a reduction of A because it is getting absorbed. Of the drug, there's a reduction of the drug. So that is with time. This means that dA by dt is the reduction of the drug. So dA by dt is equal to minus, because the drug is taken out of, however you injected the drug. So K01 into A is the amount of drug that is getting cleared from the point in which it is actually injected. So dA by dt is equal to minus K01, which is absorption rate, into A. So if you look at this, this is the first differential equation. So differential equation, because there is a differentiation, and the differentiation is accounted for by this equation. Now, we should understand that this kind of equations, first order equation, is very, very common in physiology. The solution of this equation, if you remember from the previous class, is exponential. That's why you get all the time exponential functions. Now it goes to the first, let's say, first compartment, and the first compartment has a drug, concentration of C1, and the volume of this compartment, which may be plasma, is V1. So that is the first one. And so the drug has entered here and entered into one. Okay. Now, from this compartment with concentration C1, which is, where did it get from? This compartment got the drug from the absorption rate. Okay. So the absorption rate, K01 into A, the rate at which it is absorbed. Rate means time is already there. Okay. So that divided by the volume. So amount of drug that is flowing in. In other words, drug that flows in per hour, okay, is dA by dt. So A is nothing but K01 into A. That's what is flowing in. So amount of drug increase is D into K01. This A is K01 into A. So, sorry. So this is equal to, that is increasing is K01 into A. That's how much is increasing. The rate at which it's increasing per hour. That's how it's increasing. Divided by the volume gives the concentration. So increase in concentration in plasma is because of the drug that is getting converted, is K01 into A divided by B1. Okay. So that's coming in. It's coming into this compartment. Now, from this compartment, there are two flow channels. One flow channel is that drug is getting cleared. And the other is it metabolizes. So the drug that is getting cleared is given by what is called as the clearance. It's called clearance. Clearance is the ratio of the drug elimination, rate of drug elimination, divided by the drug concentration. Okay. So in other words, this dA by dt is the first term. This term is rate of drug elimination, dA by dt, divided by the concentration C1. So look at this equation. I'll just go to the next page. So CL is equal to dA by dt, rate at which drug is getting eliminated, divided by C1. So dA by dt, what is dA by dt? Rate at which the drug is eliminated. Again and again I'm saying that. The CL clearance multiplied by C1. Now, this is the amount of drug that's eliminated, but I want to convert it into volume, so I have to divide this by V1. So that there's a minus sign here because it is getting out of that compartment. So, sorry, there is a minus sign. So that's a minus sign here. This is, I have accounted for drug clearance. So the second one is this equation where it is metabolizing. The drug is metabolizing. So let me write down this equation here. dC by d1, dC1 by dt, dC1 by dt is equal to K01 by V, V1 into A minus second term C clearance, which is going out. 0 is always going out, into C1 divided by V1 minus, because it's again going out to become metabolite, divided by V1 into C1. So this is equal to K01 by V1 into A minus CL CL10 divided by V1 plus CL12. 12 is going into the second compartment, divided by V1 into C1. I'll stop here. I'll ask questions. Joseph, you have to pardon. I'm going to repeat a few of the things so you know it, but good to hear it again. Any questions?
Yes, sir.
Joseph will answer. Okay. So that's a test for you. Any questions, you will answer. Okay.
I'll try.
Yeah, guys, ask him questions. He's quite thorough. No questions? It's a typical drug delivery system. Dr. Sundar, any questions?
Yes, this I absolutely understand, sir. After you wrote all this step by step, I understood.
Okay, fantastic.
Understood, sir.
Fantastic. So the second step is how in the second compartment, that is this compartment, metabolite compartment. So I'm looking at metabolite concentration. C2 is nothing but metabolite concentration. Is equal to, okay, what is coming in? CL12. This fellow is actually coming in. So CL12 divided by V1. What is lost in the first compartment is gained by the second compartment. C1 minus CL20, because there is a clearance here. The CL20, that's a clearance that's happening out. Okay, into C2, that is the definition of clearance. Divided by V2. V2 is the volume of the, this is the V2. So this is how this guy has gone out. So now I have, very simply, I have written down 3 equations. Okay, let me remove this first equation because that's what I've written in the next step. So the first equation is actually this equation. dA by dt is equal to minus K01 A. This is exactly what drug companies do. I am giving you a simpler example. Even today, if you see all papers, there will be multi-compartment models, more than two. So many compartments, so many conversions, so many. But anyway, the fundamentals remain the same for the drug. Okay, there is no difference to this.
Can you repeat the second equation, sir? Whether it is Cl12 divided by V, sir? Is it V?
This one, this one.
dC2 by dt is equal to.
Yeah, here, sorry, V2. Sorry.
Yes, sir. Yeah.
Yeah, because V2 is the volume of the second one. So this is the amount that has gone out. That's the amount that's gone out divided by V2 is the concentration drop. Right? Is that clear?
Yeah. Yes.
Okay. So this is C1. Right. So what was, sorry, that, yeah, that's correct. This is coming in, and then V2 is the one which is, concentration variation. So Cl12 by C1 is what came in, right? Divided by V2 is the concentration change. Note that carefully. Now, you have to understand one thing. This what the fundamental physics here is mass conservation. The fundamental physics is mass conservation. In fact, all your physiology problems in mathematical terms, for me to understand, very simple, all of them are mass conservation. Mass is conserved. Say in this case, for example, this term is the amount term. Amount that is leaving one, compartment one. Where does it go? It goes to compartment two, or it is getting eliminated. So your equations are actually simple, except Dr. Karthik's equations, which are very, very difficult, more difficult than this. If you're looking at force, you're looking at moment, looking at lot of things. Okay. So let's not share his headache. Karthik, is your headache. So, but we will look at, in simple terms, they're all mass conservation. For him, he is looking at momentum conservation. All his equations are momentum conservation. Okay, slightly more difficult to understand. And then many times we also have what is called energy conservation. For example, Dr. Sundar, you may have to deal a lot more with energy conservation. What's happening to energy? So if certain energy is produced, what's happening to the energy? Where is it spent? What is the efficiency? How much is converted actually into heat? All those kind of things. It's energy conservation. So in the whole of physiology, we will be dealing, depending upon your specialization, we may be dealing with one or more of these three things: mass, momentum, and energy conservation. Okay, so we are now looking at mass conservation. See, the whole idea is that mass conservation results in an equation like this. Momentum conservation results in another set of equations. The famous of them is F is equal to ma. Energy conservation gives rise to another set of equations. So all of them, this kind of differential equations, which we have to solve. I'll also tell you how it is solved. So now I have a metabolite. Fine. So then I have to find, Dr. Bhagyam is not interested in just metabolite concentration. She wants to know what is the drug effect. What is the effect of drug? Is the drug is going to kill the cells, the cancer cells, say for example the tumor cells, or not? So that is what is her question, right? So I have to now link the concentration, metabolite concentration, to how the drug is going to have an effect. So this is what is called as the famous Hill equation. Hill equation and its variants. These are the ones which are used for looking at the metabolite and its effect on the drug. So E is the effect, drug effect is E naught, which is, so I'll write down the equation. Sorry, let me. E max into C power X divided by E C power X 50 plus C power X. C is the concentration. C, in this case, it is C2. C2 is the concentration. Okay, so EC50 is the drug potency. EC50. The value at 50% maximum effect, value, the value at which 50% effect is achieved. It's not half-life, note that. Value at 50% is achieved. In fact, all the research is this equation on drug effect. So this is the pharmacodynamic PD part of it. Okay, so usually, so there have been a number of papers, like for example, tumor growth, number of cells, how does it vary with time, all those things. So usually this equation here is converted into an equation which results, or which can tell you how the tumor growth as determined by the killed cells can be written. So that is called as K kill. Okay, so K kill is the number of cells which are getting killed, or this drug has induced the tumor to kill, tumor to decay, and that is what does K kill. So K kill is written by K kill max into some function of C2 divided by, this is Hill's equation written in another way, K C kill 50 plus FeC2, some function of C2 multiplied by plus. So in other words, there are some constant terms that comes up, okay, in order to, and a function term that comes up, and so on. So what it simply means is that, so Fe is a function of C2. It can be some constant into C2. It can be just a constant into C2. So the effort is on by experimental work as to what these numbers are. So essentially, what we are trying to do is to ultimately look at an algebraic equation along with this differential set of differential equations, and they are called as differential algebraic equation, and you solve it to find out the rate at which tumor is reducing. So in other words, I find out the metabolite concentration C2 is what, then through a function I relate it to decay of tumor. This function is something like this, result of research on the metabolite on the cancer treatment, or that is what gives you how much of the cells are getting killed. Okay, is that clear? So these are the things which we study. Now I can go ahead. That's the first part. The second part is tissue part. I'm not going into the details of the tissue part now. So you can actually, so in other words, you can say how much percentage of tumor is reduced by the previous equation. The other is the safety part. So the safety part is, again, there are three, you can use 3-compartment model for safety also. Okay, what is the effect of drug on the skin, say epidermis? Okay, so here again, you can say that the epidermal cell, they pass through 3 compartments. One is what is called as proliferative, differentiated, and this last one is stratum corneum. Stratum corneum. Okay, these are the 3 things, and for each of these, I can write down equations. I'm not going into that. So again, compartments, even for everything is a compartment, and how from one compartment to another, drugs are moving. They're all differential equations. So that is why we have taken this as an example. Is that clear so far?
Yes, sir.
Yeah. Joseph, any questions? Everything is clear?
Yes, sir. Yes, sir.
Yeah, Dr. Bhagyam? Dr. Shanti is there?
Yes, I'm here.
Yeah,
And
any questions?
No, it's clear with this explanation.
Okay. So this is the, so if someone had, say for example, Arjun wants to look at the diabetic, in fact, digital twin for diabetic, and you listen to the talk of my student Vanilla, Arjun, you would notice that all equations what she had used 11. I mean, it looks formidable to you because there are 12 differential equations and so on, right? But all of them are only these equations. Okay, we will.
Yes.
Understood. All of them are only these equations. On the other hand, Joseph has been looking at the work of um, Rajagopalan. So on blood flow, right? So Joseph, of the 3, what do you think he is using it to you? So he has been using what is called momentum
Conservation. Yeah.
momentum conservation. So all blood flow are different set of equations, momentum conservation. Okay. So how does the blood actually, because of pressure difference, how does it flow, how the resistance act, all those things are momentum conservation equations. Okay, let's not, because this course is only fundamental mathematics course and not physiology course, I'm not going into that. This is the easiest for everyone to understand. Okay, so that is why we are doing it. Maybe later we will take that up. Now, is that clear? Any questions? Okay. See, there is one of the things that you need is what is called as initial conditions. So initial conditions are important. For example, there is no drug. So initially the drug concentration is 0, like that. Okay. So there is an initial condition to it. Now, I'm going to introduce a new concept of writing down these equations. So what is that I'm going to do? I'm going to write down. This is not able to remove it. Okay. So what I'm going to do is I'm going to look at the in the three equations which we had seen here. So the three variables are A, C1 and C2. These are the three variables. Okay. I'm going to arrange them in an array, right? So I will call, let me write down that. A, C1, C2. I'm going to put them as an array. This is called as a vector. This is called as a vector, an array. So I'm going to call this as Y. Why? Because there are three numbers there. I'll put one squiggle at the bottom. So that when I say Y1, this is A, Y2, this is C1, Y3, this is C2. So this is called as a vector, right? So actually, if you go back to that equation, dA by dt was the first equation, dC1 by dt is the second equation, dC2 by dt is the third equation. So these were the three equations. So instead of writing these things, I'm going to write dy by dt. This automatically means that there are three things involved. Automatically means, because this y is this vector. So in other words, d of a c1 c2 by dt. So this dt individually applies to everything. So this becomes dA by dt, dc1 by dt, dc2 by dt. So this, I'm going to exploit it later. I'm just telling you that I'm writing this as a vector. Okay, I'm going to just remove it. Right. So then I have a function. So what are the functions? Coming back to this. So the right-hand sides are the functions. This is one function. This is one function. This is one function. So there are three functions. F1 is minus K01 into A. F2, which is K01 into A by V1 minus CL0 into C1 by V1. That is this equation. So each one has an equation. So dA by dt, I can write dA by dt, the first equation, to be a function of C1. Look at that first terms here. It is actually only A. So I can write it as A, or I can put it as a function of A, C1, C2, but the coefficients of C1 and C2 is 0. Doesn't matter. So I can write it like that. So usually, and also time, sorry, because dA by dt, okay, that's going to vary. So some function of t, A, C1, C2, though they are not affecting in the first equation. Like that, you can write functions. This is F1. I can write function for dC1 by dt. What's there on the right-hand side? I can write it as F2 and F3. So all these big equations, three equations, I can write it in one line. Let me write it. So this is the equation, and let me write that in one line. So dy by dt, I could put a squiggle there, which means that there are three. Is equal to some function, again squiggle, which means that there are three functions. Squiggle doesn't mean three, but more than one. That's what it means. Function of t is only one value. Okay, so C1, C2, A. Instead of writing C1, C2, A, I'm going to write it as YT. That's all. Actually, this is the equation. So C1, C2, A have initial conditions. Initial conditions means what is A at 0, at t is equal to 0. initially. Now, obviously, answer is 0. So A at time 0 is equal to 0. Now, because there's no drug. Okay, concentration C1, I don't know, because yesterday you would have given some concentration might be there. So that is the initial concentration. Some metabolite may be remaining during last treatment. So that is C2. So generally you write Y at time T0. T0 is 0 or whatever it is equal to Y0. So there are 3 initial values. Is that clear?
Yes, sir.
Okay. So we have to solve this equation. Fortunately for us, it's not very difficult. It is very easy to solve this equation. So, for example, let me write down. I had written down here. So let us say that I have an equation of the form dy by dt is equal to k. I'm going to take the same equation. Dy by dt is equal to k. I want to solve this. I can solve it by what is called as the finite difference form. You remember that in one of our early classes, we said we divided the time, total time, into a number of smaller parts, say m plus 1, morning, the previous evening was m. So what is the temperature at m plus 1? Given that I know m. This is what long time back we did this. So this is if I'm going to use similar one, and it's called as finite difference. Finite differences dy by dt is what? Delta y. Remember, delta y by delta t is equal to k. What is delta y? Remember that? So delta y, say for example, if I now draw the graph, so you remember that we had a graph like this, and we wrote the slope as dy by dt. You remember that we had, okay, 2 values, say y5, y6. This can be y4, this can be y3, this can be y2, this can be y1. So these are discrete times, and of course this is time, and this is t6, t5, t4, t3, t2, t1. So these are the times, and this is the y value. Actually, that is the y value. I don't want to make it messy, so I wrote both of them down. Now, so look at this. What is this? This is nothing but y6 minus y5. So what is this? This is t6 minus t5. So if you now look at the slope dy by dt at y5, this would become y6 minus y5 divided by t6 minus t5. Okay, so this is dy by dt. Now I know dy by dt. For example, here dy by dt is equal to k. Okay, a constant. So the curve is not like that, it's a straight line. So I can write y6 minus y5 is equal to, how do I write it? K into t6 minus t5. Right? Now, I have, first it was y naught. From y0, I can calculate y1. From y1, I can calculate y2. From y2, I calculate y3. From y3 to y4, y4 to y5, y5 to y6. In other words, when I'm coming to y6 in this stage, I'm coming to this stage, I already know y5. So that y6 is equal to y5 plus k into delta t. Let's say called it as. So I know this. So this is called as the finite difference form. Okay, this is one way of writing the differential equation. I'll stop this for a minute, just assimilate it. Any questions, I'll answer it. So step by step, I am converting the differential equation into a difference form. And I am now marching in time, So first, how do I start? I start with y1. I know y0. Y0 is known. So I will write this equation. Y1, y0 is known. That is the initial condition. That has to be given. Okay, this is what we said here. Then y1 is equal to y0. The 5 becomes 0, 6 becomes 1, plus k into, I'm going to, this delta t is chosen by me. I want to, this is delta t. That's chosen by me. So y1 is equal to y0 plus k into delta t. Plus k into delta t. So I will know y1 because y0 is known. In this case, it may be 0. So once I know y1, then I will write y2 is equal to y1 plus k into delta t being the same. So this I know. So now I'll find out y2. And so this is what I am jumping from one discrete value of time to another discrete value of time. So I'm moving this. Right? Is that clear? Okay. So this is called as the Euler equations. This form of writing this equation, these equations are all Euler equations. Now, Euler is not the only guy who wrote this. There are a number of guys who wrote these equations. A number of guys who wrote. So one of the two guys who wrote this equation who are called as Range Kutta. They don't, in fact, that's at this time we will not go into what it is. They wrote a better difference equation. Unfortunately for us, we need not even know about it. So Range Kutta is what is called as a numerical scheme. Okay. So this was in the early 1900s that they came up with a scheme called Range Kutta. Okay. Range Kutta in the early 1900s, that is available in every software. Okay. So there are enough, let's not worry about too many things. Now, RK method. The RK method in MATLAB is called as ODE 45. ODE 45. Now, let me explain a simple way of solving this problem. Very simple equation. Okay. I'm just going to consider only one compartment. Only one compartment. So the one compartment model consists of two terms only. So that compartment's variation is dc by dt. Compartment's concentration variation is dc by dt. Okay. So the dc by dt variation of that compartment is what concentration what you are giving as a dose minus what is getting cleared. Only two terms, coming in, going out, mass conservation. That's all. Okay. Now, you are giving, say, IV intravenously for a time, say, 2 hours. So you have told your attendant or the nurse that you have to give 200 mg in 2 hours. So the rate at which the drug is going in is 200 divided by 200 per 100 mg per hour. And then once it's 2 hours, you say stop it, 0. So this is the equation for the drug which you have asked your assistant, whoever it is, to be given. So dose in 2 hours. After 2 hours, it is equal to 0. This is all you give. So that is the equation here, divided by the volume is actually the concentration. So how do you find out, say, for example, blood volume? How do you find out blood volume? How do you find out the blood volume? Like this simple thing. So you get a tracer, or you get something, which goes into the drug, into the body, a drug, whatever it is. And then once you give it, you find out. Yeah. You then find out. Okay. You find out what is the concentration of that drug in blood. So you know the concentration. Okay. So once you know the concentration, you know how much of drug you have given, divided by the volume is the concentration. This you know, this you have given. So V is equal to A by C. So you can find out the volume of blood from this straight. That's all. So let us solve this equation using Angekutta method. I'm going to go out and then get my MATLAB code. You're able to see my screen?
Yes, sir.
MATLAB screen is visible?
Yes, sir.
Yeah. Okay. Now, what is that we have done? So this is the infusing. The number of, one compartment, there's so many things. So what is that I want? I want what is that concentration with respect to time. Okay. Just let me run it. I hope it runs. Yeah. So this is what I have given. Say for 2 hours. This is the 2 hours. I have given this. So this is the concentration of the drug with respect to time. So I've solved the equation which I wrote, and so I got to see this. This is the curve, concentration with respect to time. Right? Now, let's look at the how I have done this problem. Again, you can use ChatGPT, but this is very easy problem, so I'm not using any of this. So there are actually two variables, volume and clearance rate. Right? So let us say that the volume, blood volume is 12.6 and clearance is 2.16. That is the clearance. Okay. After percentage, it is a comment. Now, I have used an array called P. You remember that big array I had put Y? Here, I have called it as P. So P dot P means the first entry in that array. called vector. P dot CL means second entry. There are only two entries there. Okay, it's 2.16. Right. So this is the equation. You see that. That is the equation which I will be solving. This is called ODE 45. So there are basically three entries or four entries. One is, what is the equation? You remember our equation? Right? You remember the equation which we used? dC by dt is equal to R of T by V minus CL into C divided by V. That's the equation. Right? So derivative. So this is the equation. Look at that. So this is the derivative. Okay. So this derivative is what is written here as a function. So derivative is a function. Okay. Function dc. This is what is. So when you call a function, you call at derivative. So this is the function. Okay. Now, so that is here. I'm going to do this for, say, 15 hours. And initially everything is 0. And what is called as P consists of two entries, 12.6 and 2.6. So instead of writing volume and clearance rate, I put both of them in a vector with two entries and use P. That's all. Over. Okay. Now, these are all plotting. So let's not worry about plotting. You can always learn that plotting. So the derivative is the equation. Now, if you look at that equation, there is one function in that equation which is called RT, which is how you have asked your guys to give dosage. So that function here is given here. And this states that star t less than 2 means that I am giving till it reaches 2 hours, I'm giving 200. So the rate at which I'm giving is 200 by 2, 100. You saw that. After 2 hours, once this 2 hours is crossed, 0. There is nothing I am giving. That's what it means. Okay. So whatever I have written now, nothing more than that. There is one command which you can mug up. There's no problem. There's a command you can use it all the time. Then these two. So I had run that code, and then I clearly got how does the concentration vary. Look at it. So as long as this IV is flowing, the concentration keeps on increasing. Now, when do you decide to stop? Actually, you should look at the concentration. So the concentration reaches what you want, it drops, stops, and then the concentration starts decreasing. Is that clear? Any questions? Any questions?
So the square bracket in the ODE function before P.
This one.
Yeah. And at the end, after 0 and between 0 and P, there's a square bracket.
Yeah. So there are a number of terms to this. Okay. What I would say, why not? There are some options. Let me put it like that. There are some options in it. Okay. That options, I'm not using those options. Okay. That options are what that is given. So the options can, sorry. Right. The options, you can use it. When you put a square bracket like that, no option is used. That's what it means.
Okay.
Okay. So there are, well, let's not worry about what are the options now and so on.
Okay.
I'll just say that there are options to it.
Okay.
Okay. Yeah. Most of the time we may not be using those options. Right. Does it, you understand? Nothing.
Yes, sir.
There's only one function. That's all. The derivative, you just call it. And the derivative, whatever I've written this as simple code. I'll send you this code so that you can look at it again and again. You will understand what it is. In fact, you can try it out writing this in ChatGPT. You will get a similar one, almost the same thing as you see here. So it will also choose ODE45 straight away. ODE45 is one of the major schemes to solve differential equation solver. Okay.
Yes, sir.
Okay. We can keep making this more difficult. I think my second one is delay differential equation. Yeah. Okay. So now equations can make it, we can make it more difficult. So what do you mean by more difficult? I'll come out of this and I'll go back to my iPad. 1 second. Where is this? Okay. I'll stop sharing. So I'm sharing my screen here. So look at the beauty of it. So we can have another situation, sir. Yeah. Another situation where, say, there is a delay. Most biological phenomena has a delay. Okay. So what does it mean? It means that there is a delay which I will call as tau. Okay. So when you give some dose, you may not see immediate effect. There can be a delay in absorption. Right. And this is always the case. So then the same dy by dt can be written slightly differently as a function of t, of course, with the y's with a delay. Okay, with a delay. Tau f is what is called as the delay. Then we call this as a delayed differential equation. So what does this mean? Let's take our simple examples. Let's say that I am injecting a drug A. This is what I'm injecting, amount I'm injecting. So A is function of T. Remember that dose, that's what it is. Or R of T, A of T, we use that. So the rate at which actually it is getting cleared, let's say, is K into A of T. Cleared means it is getting into the system. Then dc by dt of the first compartment, only that compartment, is K, I'm just going out, into A of T. Okay. And divided by V, that is a dc by dt. Sometimes people use bioavailability also. Yeah. Minus, look at this equation is more important. This part is clearance. C, T minus T lag. So what it simply means is that the concentration, there is a lag between the concentration that's available to concentration decrease. There is a lag that is called T lag. Clear? So there is a lag. There is a delayed drug. We call this as delayed drug concentration. There's a delayed drug concentration. So there's a constant clearance, but there's a delayed drug concentration. Okay. So this equation can also be solved with delayed drug concentration in a very similar fashion. So let us now look at how to solve this equation. It's a simple equation that solves, that is solved using what is called as a delayed differential equations, DDE, delayed differential equations. Now, delayed differential equations, like ODE, are again a part of the MATLAB. Okay, they are also a part of MATLAB. So these, instead of ODE 45, is what we used. Remember, that is the term we used. Here it is DDE 23. Now, this is slightly advanced. So if you understand well and good, you're not going to do it. If you don't understand, don't worry too much. Okay. So nevertheless, we are using what is called as DDE 23. Now, there is one small addition to this. We will see what that addition is in a minute when we go to the program. So I'm going to stop here and I'll go to the program. I'm going to stop sharing the screen. And I have to share the screen in the okay. You're able to see my screen, right?
Yes, sir.
Yeah, in the other one I can also see. So this is the function. When in order to call the function, I say DDEMR, then it calls delay differential equation. So I'm going to close everything and then I'm going to do this. Let me see, I hope it runs. Yeah, okay. I'll explain this. Now, I'm going to have, what is P? You remember? P is a vector. P has had 2 entries last time. Now I'm going to have 4 entries. So what are the equations I got? Remember, just now I wrote it. What are the equations I wrote? So
dc by
dA by
dt.
dt is equal to minus k.
Okay.
So what are the things that were available? K or Ka, that multiplication term. Okay, that is the clearance rate or removal rate rather. So K, this is K, volume, initial volume, blood volume, clearance rate, CL, and then bioavailability. Just I put it because many people put that. I just put it as 1. So put F is equal to 1. That equation. Okay, now I have to put initial concentration. So initial concentration is 0. Okay, that is initial concentration is 0. Initial amount of the drug at T is equal to 0, I have given 100. This is just I have given 100. At time T is bolus 100 microgram I have given. At T is equal to 0. Okay. Now I'm going to look at for say 60 minutes what happens. So I'm going to use what is called as the delay differential equation. This is the DD. A derivative similar to the previous one. So I'm going to use a lag, 3 lags. Lag of 1 minute, 2 minutes, 3 minutes. Okay, so I'm going to use 3 lags. That's what is here. Si dot a lag means there are 3 lags. So when I put dot, it immediately is a vector. Okay, that's what it means. So I can use all the 3, or I can put here. For example, I can separately do. This is the delay actually. Delay can be 3 minutes. I can just substitute this by 3. Then I'll get only one value. Instead of that, I am putting all the 3 values. Don't worry if you don't understand now. Doesn't matter. I'm just only showing you it can be done. Slowly have a look at it. You may understand it. It's not necessary that you should completely understand this. I just want to tell you that maybe people like Johnson or um, Arjun who's going to delve deeper into models, they need to know. And that is the reason why I am taking this. So just listen to what really. So in other words, what is that in total? What is that I want you to understand? I want you to understand even if there is a delay in drug reaction, you can solve it using simple method. That's all I want. Okay. So now, so this is the equation. So you have what is called as options here. T span is what is given here. Option is, there are 2 things. Because of the way actually the algorithms are written, the delta t, what we have used, is a finite number. Actually, if you remember, delta t has to go to 0, delta t tending towards 0. So it's a finite number. So because of that, there is an error. Okay, there is an error in the components of y because it's not actually, it's a finite value. So the size of that error, there are 2 of them. So that error size is what I am giving as 1 e power minus 6 in both relative uh, error tolerance as well as absolutely for individual component. Okay, both of them I'm giving, don't worry about it. This is the error term for delta t being finite. Understand that. That's all. Okay. So now all those things are similar. So let's look at the result. So this is actually the concentration with respect to time. It's a very, actually, if you look at it, it's a very interesting curve. So you can see that, so 60 hours rather, not 60 minutes. So it's in terms of hours. So you can see that when delay is 3, there's a delay of 3 hours, then the concentration actually increases. Because the concentration drives the reduction, look at that. It reaches a maximum, comes down faster. So the lower the concentration, slower. Why is this? Can someone tell? Joseph?
Because dA by
So,
dt is function of A by A. The change is function of the amount itself.
exactly. So because dc by dt, concentration keeps increasing because there's a delay in its reduction. Clear? So concentration keeps on increasing, it's not going out. So higher the concentration, then it starts working faster. Clear? Okay. So don't worry about this equation. I'm going to give anyway, Josen and Arjun, I'm going to, for you, this may be interesting and important. I'm going to give this to you. If there is any doubt, we will discuss it separately. Okay. So I'm going to give this. The reason why, I mean, anyone can do this. I'm not saying, but I don't want to scare you by giving this. That is why I'm telling for others that, I mean, you are also free to look at it, ask questions, all that, but I just don't want to scare you with more complex equations. So just wanted to tell you that delayed part also is possible. That's all. Okay. Any further questions? So if you remember, we had a differential equation and we had an effect of that differential equation as a algebraic equation. Clear? So let us solve a simple differential algebraic equation. This may be very important for many people who are working in cancer, who are working in drug reduction, say, for example, whatever you want. Dr. Shanti may use a drug for, say, for a viral infection. All those things, all those drugs are controlled by differential algebraic equation. There's a drug, there's a concentration. The concentration is not what you are interested in. Concentration has the effect on virus or bacteria rather. Then that is what is your interest. How does concentration kill that bacteria is what is your interest. So let us now look at a very simple equation in this respect. This is again simple pharmaco PK model. I'm going out of this. So just what I'll do is I will post this in the I'll stop sharing. I'll post it in the group. Please see it. If there's a problem, I'll explain to you. Okay.
Okay, sir.
And you can always put this in ChatGPT. I ask ChatGPT to explain, it will explain. Many things I also learned like that only.
Yes, sir.
Okay. So let me share the screen. Right, done. So okay. So why is this coming all the time? I don't know. Okay. So first equation, let's write dC by dt is equal to, I am giving a drug volume, so that concentration minus K into C. That is the first, variation, drug concentration. What is going out is minus K into C. What comes in is this. Now, I have another equation for effectiveness of the drug, which I would write a simple equation, E max by C divided by E50 plus C. So I have some values. Initial concentration is equal to 0. Maximum is equal to 20, E max. These are values obtained from experimental work. E50, maximum E50 is usually half of it, 10. Or not, what I'm giving is 1. And K is equal to 0.1. And volume I've calculated as 6. So this is the data for this equation. Okay. So this is the PK part. You would have heard about pharmacokinetics and pharmacodynamics. So this is the PK part and this is the PD part. So both of them together is PK-PD. That's all. Very simple, not very difficult. This whole PK-PD, as that day Joseph was telling, you can mint money with, if you know this, okay, and they're not very difficult to even understand. They're all mass conservation equations. Okay, so now I can write down the way I had written down before. First y. What is y? I have to write it in a vector form. C and E. This is my y. Okay, then dy by dt is actually just to complete it, dc by dt and de by dt. Actually, this, if I write dy by dt, it is dc by dt and de by dt. Okay, now I have to solve this equation. In order to do that, I have to introduce some concepts which are new, which I'll do that in the next class. We'll stop here, which I'll do that in the next class. Okay, on what is called as matrix before we come back and look at these equations. In fact, by the end of the course, I would confidently say, if you understand it, your maths level should be quite good to understand most of the thing. Whatever your area you are going to work, maths is going to be helpful, and it will definitely be of great use. Okay, the only thing I want you to look at is okay. I'll do that. I will do that in the next class. Okay.
Yes, sir.
How do I write? Okay, one question is, how do I write d by, what is d by dt? Okay, we'll see that in the next class. What is d by dt? E is, I know. What is d by dt? Why am I writing it? All those things. We'll see that in the next class. How to solve this equation. Okay, so any questions? So I'm interested in both concentration as well as the effect. Simple equation. That's what I'm going to solve. Okay, I'll do that in the next class. And before that, any questions? Okay. This will be, I mean, one or two will be slightly difficult to understand. You can, I mean, it's an option. If you're going to work, you can take it, or you can just understand that these kind of equations exist. Differential algebraic equations, it exists, and it can be solved. That's all I want you to know. Don't worry as to what or how this is solved. Just to know that there are, because as Joseph was that day telling, that this group may be a mixed group. Some of them may go deeper into maths, or some of you may not be interested in so much of maths, but nevertheless, it doesn't matter. I am giving you a background. Whatever you can absorb. If you don't absorb some of the things, don't worry about it. It's not required. Okay. So I will teach you how to solve this problem in the next class. Again, using only MATLAB. Right. So I'll stop here because I need to go into some other new topic. So I'll stop here and we will continue next class. Okay.
Yes, sir.
Please have a look at it. If there is any questions, definitely we will answer that questions before we go to the next topic. Just this is the last one I'm going to do in differentiation. Then I'm going to move our differential equation, and then I will move over to another topic, okay, which is very useful, which forms the basis for all machine learning, AI, and all that. So that would be the next topic. Slightly advanced topic. If whoever is interested, I will have a more special class. And if you understand, if you want to attend, we will do it. Well, Joseph will do it like that.
Yes,
Slightly
sir.
more advanced topic. We
Yes,
will
sir.
have a class, and whoever is interested to attend, they can attend, because it may not be required for everybody.
Okay, sir. Yeah.
Okay, whoever is interested, they can definitely attend. Right?
Yes,
So we'll stop here. Please go through it. If there's any question, we'll again discuss this in the next class. Okay. Essentially, I've learned a good topic called differential equations. Okay. So stop here. Good night. And we'll meet.
Okay, sir.
I have not
Yes, sir.
given any assignment. I will do that after. I'm going to stop with the next class and then give a lot more problems. Whatever I have done, I'm going to cover in next. After that, maybe even starting from next class, I'm going to give a lot more problems to understand whatever I have done so far using MATLAB, ChatGPT. That's it. Okay. Thanks.
Thank you,
Thank
sir.
you.
Thank you,
Thank you,
sir.
sir.